Welcome back for the second video. In this video, we'll go over 6.1 Probability Distribution Introduction and how you can complete March 20th attendance quiz, where you will find the link in this slide right here. Alright, let's open up the slide. Let's see if I can present. Okay. So we are now starting chapter 6, and it's about probability distribution. And later I will get to talk about normal distribution and binomial distribution, but this slide is just for the introduction, what probability distribution is and what random variables are. The first learning objective that we need to go over is distinguishing between discrete and continuous random variable. And in fact, you did something very similar with just variables, discrete variables and continuous variable. So I want to do that one more time. I'm just going to call them random variable this time, but let's talk about what random variables are. A random variable is a numerical outcome of a random phenomenon. What does that mean? I got about 4 examples ready for you to talk about these. We're gonna create a random distribution frequency table, and also may just introduce you to the probability mass function too. So I got 4 examples on what these random variables are, but let me give you a couple examples, the short ones first. Now, suppose that you're flipping a coin. Okay, flipping a coin. You can get, let's say, say that the event that you're interested in is getting a tail. So what you can do is every time you get a tail, you said that's 1 tail. Every time you get a head, then that will be 0 tail. So just a quick example of coin flipping, a random event of getting a tail or head. I think the first example, a couple more here. So say that we're tossing a coin 3 times and let X be the number of heads. So if you're tossing a coin 3 times, how many hits can you get? You can get 0 heads if everything comes out to be tail. You can get 1, 2, or if all 3 tosses come in heads, then you can get 3. So X is a random variable whose possible values are 0, 1, 2, and 3. So X ranges from 0, 1, 2, and 3. But this one later we'll talk about how it's going to be discrete, because you cannot get 1.2 or 2.7 number of hits. Okay? Another example. Take a simple random sample of size 30 from the population of NOVA students and let Y be the average GPA of the sampled students. So what could be that range? If for some reason, if you're very unlucky and we get 30 students with 0 GPA, everybody got 30, like a 0 GPA, and that can happen, right? Because it's simple random sample. If that happens, the lowest GPA average will be 0.0, but on the very extreme, like happy side, what if you got 30 students whose GPAs are all 4.0? Then their average will be 4.0, right? Their average will be 4.0. But here's the thing, it can be anything in between. And when we're taking the average, it can be all these decimals. And so here, Y is a random variable whose possible values are the numbers and the interval from 0.00 to 4.00. In this case, I know we're rounding up to the nearest hundredth here, but it can be any number in between those two. So we will say these are going to be this is going to be an example of continuous random variable. So random variables can be continuous or discrete. Well, guys, I'm playing with these animation feature on Google Slides, so you'll see how I'm going to use that more and more on my videos. So let's talk about the continuous one first. Continuous random variable, the sample space is going to be continuous, like an interval. So for example, like when you take the measure, like height or weight, I'm about now what? 135 point blah 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 pounds now, but it's never going to be 135 or 134 exact, right? So any measurement, weight or height. Or specific example here for you. Take a random cow and let's milk that cow. The volume of milk produced by that cow is going to be an example of continuous random variable. Another example of continuous: hours spent on sales calls in one day. If we say, because we're not going to say 1 hour, 2 hour, 3 hour, we can say something like 7.45 hours spent on sales calls in one day. So if we use hours, like time, that's going to be another example of continuous random variable. Now, discretes are the ones that we're going to look at more today in this slide. Sample space is separated. So, for example, the counts, anything like 0, 1, 2, 3, like the number of sales calls a salesperson make in a day. Either he makes 10 calls, 12 calls, 11 calls. We're not going to say he's going to make 11.75 calls. Another example, the number of fish caught on a fishing trip. We're not going to say 7.5 fish just because you almost caught it. We're going to say 7 fish or 8 fish or 9 fish. So those are examples of discrete random variables. So let's do an example. Determine whether each random variable x is discrete or continuous. Let me read number 1. Let x represent the number of Fortune 500 companies that lost money in the previous year. What do you think? That number is going to be just like a whole number, right? A whole number. So it's going to be like 10 companies or 7 companies or 450 companies. So in that, the first one, the answer is going to be discrete random variable, because we're not going to say 375.4, or it's not going to be a decimal value. It's going to be just a number value, a whole number. Now, number 2, let x represent the volume of gasoline in a 21-gallon tank. Now, it can be from 0 to 21, anything in between. So this one is going to be continuous random variable. On the Google form quiz that I will ask you to complete on this Friday's attendance quiz, I got a couple of these questions for you to answer on continuous or discrete random variable. Now, let's work with discrete random variables for the next couple examples. I'm going to create something called probability distribution frequency table. And I didn't really make this into numbers yet. I'm going to go ahead and just use the colors. Colors are categorical variables, right? Now imagine spinning this spinner. I can see that there are yellow, blue, red, and green colors that we can get. We're more likely to probably get green, right, than yellow, because there are only 2 yellow slices and there are 4 green slices. But I said S. The sample space is either yellow, blue, red, or green, nothing else. Take a look at the notation, x of s. Okay, so let x of s be the random variable that the color landed on. Take a look. I'm going to create a probability distribution table. On the left side, you will see 4 colors listed: yellow, blue, red, or green. What is the probability that we'll get a yellow slice? Let me spin it. Notice there are only 2 yellow slices out of how many? Let's count the total. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So out of 12 slices, there are 2 yellow slices. So the probability of getting a yellow is going to be 2 out of 12. What about blue? There are 3 blue slices, right? So that will be 3 out of 12. And for red, I can see there are 3 red slices again. So it's going to be 3 out of 12 again. And lastly, green. We have 1, 2, 3, 4 green slices. So that will be 4 out of 12. Now notice I didn't really simplify the fractions here. Now the probability, and we know the rule for probability, they're never going to be anything greater than 1 or less than 0, and you shouldn't get any negative. But what happens if you add these probabilities together? If you add 2 over 12 plus 3 out of 12 plus all these together, you will get 12 out of 12, right? So remember that rule still applies the same. That same rule still applies. The sum of the probabilities should be 1, and nothing should be smaller than 0 or be greater than 1. You can have 1 in one column and everything else can be 0. That's possible, but it shouldn't be greater than 1 or less than 0. All right, now using this distribution table, I am going to create something called a probability mass function. Take a look. Look at the the left column as your input, okay? If you plug in yellow, the output will be 2 out of 12. If you plug in either blue or red, the output will be 3 out of 12, right? They are the same. If you plug in green, the output will be 4 out of 12. So this is how we can write the probability mass function. It's called PMF. And it's a piecewise function, right? Because depending on what you plug in, if you plug in yellow in there, you will get 2 out of 12. Either blue or red gave us 3 out of 12. And then the green, if you plug in green, you got the probability to be 4 out of 12. Take a look at the very last one. Any other color, which was not even listed on our spinner, the probability of getting, let's say, a random number of hot pink is going to be 0. Okay, so probability mass function, also called, abbreviated as PMF, it's nothing more than creating a function from our distribution table. Okay, all right, let's look at another example. I think I have about like 4 examples in total in this slide. All right, experiment. Let's roll a die, single die. So if you roll a die, the sample space is going to be either 1, 2, 3, 4, or 5, or 6. But let's do something fun. Let's make our random variable to be the square of number rolled. So say that you rolled 5. You're going to square 5. So if you get 5, the outcome will be 25. So here you go. We have if 1 is squared, you get 1. If 2 is squared, you get 4. If 3 is squared, you get 9. Guys, should we have 26 right there? What did I mean to type? I meant to type 36, right? Let me fix that real quick and we'll come back. It should be 36. All right, that's good now. So the random variables are going to be, the sample of these random variables are going to be 1, 4, 9, 16, 25, and 36. And that's it. We're not going to get 49 because we don't have 7 on the die. All right. So here is the probability distribution table. X can be either 1, 4, 9, 16, 25, or 36, but probability of those numbers showing up is going to be 1 over 6 no matter what, right? If it's a fair die. So if I write it as a probability mass function, for x's 1, 4, all these x's that we can get, the probability is going to be no matter what 1 over 6. It's a fair die. Now, probability of getting something else like 49 or let's say like 5. Notice 5 is not a perfect square. So anything else will be 0. Okay, that was a short example. Now let's make this time let's roll 2 dice. Okay, suppose you roll 2 dice. What we're going to look at is the sum of the rolls. So let me explain this table that I created. Say that on my first die I rolled 2. Okay, say that on my first die I rolled 2. Say that on my second die I rolled 6. Then the sum of the rolls is going to be 2 plus 6, which will be 8. So the yellows, the columns in the first row and the first column that I shaded in yellow are the numbers that you will see on a die or dice. The white ones, these are the numbers that you will get if you add them. So what's the smallest sum that you can get? The smallest sum will happen if you roll 1 on the first die and 1 on the second die, right? So if you do that, 1 plus 1 will give you 2. So the smallest number that you can get is 2. What's the biggest number you can get when you add these two numbers? That happens when you roll 6 on the first die and 6 on the second die. 6 plus 6, that will be 12, right? But now there are more than one ways to roll dice and get their sum to be, let's say, 5. Now notice this diagonal right here, 5, 5, 5, 5. What they're saying is I can roll 1 and 4, they add up to 5. Or I can add 2 and 3, they add up to 5. I can roll 3 and 2, they add up to 5. And 4 and 1, they add up to 5. So it's more likely for us to roll, let's say, and get their sum to be 7, which I have 1, 2, 3, 4, 5, 6 different ways, than rolling a die and get their sum to be 12. I hope this table makes sense. Now let's create a probability distribution table right here, okay? So what's the chance that their sum comes out to be 2? Now, what's the sample space here, guys? Count how many possible outcomes we have in this table. We have 6 rows and 6 columns, so 6 times 6, the sample space is going to be 36. So out of 36, there's only one way for us to get 2. Okay? That's when we roll 1 and 1 on both dice. So the probability is going to be 1 out of 36. Okay? Now, what about rolling and get their sum to be 3? And there are 2 possibilities, right? Either I roll 1 on the first, 2 on the second, or 2 on the first and 1 on the second roll. And so therefore, since I have 2 different ways to make that happen, I'll say that the probability is going to be 2 out of 36. Now we continue this all the way up to 12, and I got the rest of them filled out for you. It's pretty fun. Take a look. It goes up 1, 2, 3, 4, 5, 6 out of 36. It's the chance of us rolling and getting their sum to be 7 is going to be the highest. There are 1, 2, 3, 4, 5, 6 different ways for their sums to be 7. But notice how we go bigger, like 8, 9, 10, 11, and 12. The numbers are getting smaller. So imagine graphing this. I don't know if I graphed it. That will be fun. Oh no, I did not graph it. But say that you graph this probability distribution table. That's going to be a nice symmetric bell-shaped curve, really. I don't know if I can say bell-shaped. I'm not going to say bell-shaped. I'll just say a symmetric curve with the lower on the left is going to increase and it's going to decrease. But it's going to be a perfectly symmetric graph. Maybe later I'll add a picture of this. But I know for sure, number 4, I included a graph of this distribution. Example 4, let's construct and graph this discrete probability distribution. The first 3 that we looked at were theoretical probabilities. Now this one is not. Let's read what this is about. An industrial psychologist administered a personality inventory test for passive-aggressive traits for 150 employees. Each individual was given a whole number, score from 1 to 5, where 1 is extremely passive and 5 is extremely aggressive. Ooh, okay. A score of 3 indicates neither traits. So I think I'm like, I don't know, 2. I'm not really aggressive. Anyways, the results are shown below. Now, I know there are 5 outcomes. So if you're thinking like theoretical, mathematical probability, you're probably thinking 1 out of 5. 1 out of 5 each of these. But as you can see, they're not all 20%. The first one is 24 out of 150 people. So the first one is approximately 16%. The second one is about, let's say, 33 out of 150, that's about 22%. Now, this isn't theoretical, this is empirical probability. This is actually from the data. Now, what do we do with this? Let's create a probability distribution table. And as you can see, I got this already filled out for you. Take a look. Number 1, I'm going to do 24, and I got that frequency from this table. 24 out of 150, because we surveyed or we tested 150 employees. 2 is going to be 33 out of 150. 3 is 42 out of 150, but notice all these numbers are less than 1, but they're all positive numbers, right? Now, in fact, they will add up to, if you add all these numerators together, you will get 150. And 150 divided by 150 will be 1, and that's going to be 100%. So that's how we make the probability distribution table. And if I graph that table, look. Scores 1, 2, 3, 4, 5, and we made the width to be the same. 24 divided by 150 is approximately 0.16. So notice this bar goes slightly above 0.15, and the tallest bar right here is for those people who scored 3. 42 divided by 150 is approximately it's exactly 0.28. That's why the bar goes up here. So this is how you can make a distribution table into a histogram. If you want to talk about the shape of this distribution, I will say approximately, symmetric. let me read this because I typed it. Because the width of each bar is 1, the area of each bar is equal to the probability of a particular outcome. Also, the probability of an event corresponds to the sum of the areas of the outcome included in the event. You can see that the distribution is approximately symmetric. When we talk about normal distribution, we will have a we're going to have a curve, and we will calculate probability from the curve, not really from a histogram, but we'll talk about those continuous random variables in next lesson, okay? All right, so discrete probability distribution must satisfy the following conditions, and we talked about this as we were looking at those examples. The first one, the probability of each value of discrete random variable is in between 0 and 1 inclusive. So nothing negative, nothing bigger than 1. But it can be 0 or it can be 1, okay? The second one, the sum of all probabilities better be 1. If they don't add up to 1, then it's not going to be a good probability distribution. We're going to be missing 1 or 2. Okay? So let's verify if this table that I gave you is a probability distribution. What is this about? This is a distribution for the 3-day forecast and the number of days of rains. Okay? So if we're looking at 3 days, we can have 0 rainy days. And that one probability was 0.216. I can have 1 rainy day, 2 rainy day, or 3 rainy days. Now, what I want you to do is I want you to add all these numbers together and see if they add up to 1 first. If you do 0.216 plus 0.432 plus all those numbers added together, they will add up to 1. So that passed the second condition. But also notice all these numbers all these probabilities are in between 0 and 1. Nothing is bigger than 1, nothing is smaller than 1. So this is a probability distribution. This one is a good one. All right, let's look at 2 more. Look at the orange one first, okay? Look at this one. Now, what I like is this. I see that all these numbers are in between 0 and 1. So that's good. But then the second thing that you have to check is add them all. Add them all and see if they add up to 1. If you add 0.2, hold on a second. I typed in 0.25. It shouldn't be 0.25. It should be 0.28. Let me fix that real quick. But I'm sure I typed this okay on my calculator. But let me double check. Vera, double check for me. 0.28 plus 0.21 plus 0.43 plus 0.15. They add up to 1.07. So they need to add up to 1. And the fact it didn't add up to 1, well, we're looking at something that is not a probability distribution. So this orange one on the left side is not a probability distribution. Now let's look at this gray one. Automatically, we know this is not true. Just because, well, look at this probability. Probability of rolling a 4 is -1. We shouldn't get any negative probability. And if you look at this one too, 5 over 4. 5 over 4 is actually 1.25. That one is greater than 1. Now, if you add these together, though, just out of curiosity, if you add these together, I bet they add up to 1. Let me see. I learned that I can use this document camera to show you what's on my desk. So if I add up 1 over 2 plus, I already know this is not a probability distribution, so I'm just doing something. So 5 over 4 plus -1. If I add all these together, you know what? I do get 1 as a total, but it's still not a probability distribution because 2 of the probabilities listed in our table didn't meet the first condition. They have to be greater than 0 and less than or equal to 1. But as probability of 3 is 5 over 4 and probability of 4 is -1, this is not a probability distribution. Now, that's it. That's it for the introduction. Now I want you to, based on what we just talked about, I want you to complete the attendance quiz that I created on this Google form. So click the link. Type your name for me because it's not going to automatically collect your email address. So type your name, answer number 2, 3, 4, all the way down to number 10, and submit it for me. I can't submit it because I'm going to ask you to answer every question. So try this. when I get your results. Let's see if anybody actually tried it already. Probably not, because I'm still recording it. So no responses just yet. If I get your responses here, I will see your name, and if you get at least out of 8 questions, oh, get me 8 out of 8, please. So if I see your name showing up here, I will mark you present, and that's how you can get your attendance credit for this week. Okay. Please come back and please come back for 6.1 mean variance, standard deviation, and expected value video in about, I think I'll have it in about like 30 minutes. Okay. All right. My goal is to have everything posted by 2 o'clock today so that you guys can start working, but everything is due next Thursday. So today is the 20th. Everything will be due March 26th. I'll stop the video for this now. Okay. Thank you.